So this is an example and lesson of how growth and decline with populations work. So in this video, I'm going to talk about an example with a disease, and I'll get to this example in a few minutes. If you want to pause and read it, you can. But I'm going to kind of give you a brief lesson because this example we could really change it to like disease, populations, like bacteria samples, whatever you want really. So this model applies in a lot of different ways. So really the idea here is that in general, when quantities increase or decrease at a rate proportional to their size at a given time t, we say these quantities experience exponential change. And so this is actually how you would model that kind of scenario as a differential equation. So this is talking about the rate of how some quantity changes over time. And so this is really expressing like how that's proportional. So the first thing that I want to do here is I want to talk about this differential equation, and I want to find the solution. So the thing to notice with this is that this is a separable differential equation. So what that means then is I want to get kind of my y's together and then get the t maybe on the other side, so separate everything. So I can divide both sides by y to get this 1 over y dy dt equals k, and then I'll bring the dt to the other side. So this is how I can separate everything, and from here I can integrate. So if I integrate, I get the natural log of y equals kt plus c. And so what we want to do here is we need to solve this for y. Okay, so let's focus on this expression now. So really the only way you can solve for y is by using the definition of a logarithm. So if I use the definition, this is how I can rewrite this expression. And so now what I'm going to do is I'm going to focus on the exponents for a moment. So I'm going to split this up into e to the kt and e to the c. So I could still add these together by using properties of exponents. But in doing this, I can think about now this e to the c. And so this is really just a constant, right? So c represents some number, and if we had more information, we could figure it out. Right now, it's just kind of a placeholder. So ultimately, e to the c would just be a number, just be constant. So we're going to rename it. Instead of e to the c, we're going to name it y sub 0 or y naught. So rewriting this expression, here's what I'm going to have. And so this is the general solution for really unlimited population growth or decline. So you have growth if k is greater than 0, and you have decline if k is less than 0. So you can very quickly tell if you have growth or not. Okay, so like I said, this applies to the decline or growth of diseases, populations, bacteria samples. It really doesn't matter, like as long as you have kind of that decline or growth scenario, you can apply this in a lot of places. So in this video, what I'm going to do is I created an example around the very timely pandemic that we're in, and just thought this would be kind of interesting to talk about just the math of this. So back in April of 2020, I pulled the number of coronavirus cases at the time. So that was 2,660,000 were active. So here's like, let's pretend that we stabilize this and we want to start now decreasing the disease. And let's say that we can decrease the number of cases of the disease by 50% in a year. So if we do that, how long is it going to take to get the number to 2,000 cases? Okay, well, what we're going to do here is we're going to use that solution that we just talked about. So this thing that we just created, this is where this applies. So we don't even need a differential equation in this. Like we already did all that work to find the solution. So now we're just going to use that solution. So the first thing to notice here, and with like any type of population problem, they're going to talk about where you're starting. So in this problem, we're starting at 2,660,000. So I'm going to plug that into my equation. And now if I kind of go on with the problem, so this number of cases can be decreased by 50% in a year. So let's translate that to kind of this equation. So if I take half of the number of cases that we have, so 0.5 times that 2,660,000, this is going to give me 1,330,000. And so now this can actually really be input into this problem. So let's do that. So now I've got in 1 year, I should have half the number of cases. Okay, so now that we've got that set up, we can actually just solve for k. So I want to focus on this. So I've got this situation here. So to get k by itself, first things first, I need to divide both sides by that 2,660,000. And so in doing that, I get 1/2 equals just e to the k. So the only way to solve for this now is to take the natural log of each side. And when I do that, I can bring this k down using properties of logarithms. And so now the other thing to notice here is that the natural log of e, that just equals 1. So actually this just simplifies then to k just equals the natural log of 1/2. So nice and simple. So going back to our example, so now I can really take the model, like we have a much more robust kind of model we've created. So this is kind of the model that works for this situation, because now we've solved for k. So I just want to review now kind of what we've done with this problem. Like after you work with a problem for a while, you kind of have to go through and review where you're at. So we used this piece of information, so that's all good. And we've used this piece of information, right? So the piece of information we haven't worked with yet in this problem is this bit about the 2,000 cases. So this is asking how many years will it take to get the number to 2,000 cases. So the 2,000 really needs to go here for the y. So if I plug that in, I get this situation. And so now I can see here that I have to actually just solve for t. So to solve for t, I can divide both sides by that 2,660,000. And I'm just going to reduce this fraction for now. I'm going to leave this in its fractional form for a moment. So I can reduce that fraction to 2 over 2,660. So just again, reducing. So from here, now I really want to just do the legwork to solve for t so that we can answer the question. So let's just focus on this for a moment. So first things first, to solve this. So, you're going to have to take the natural log of each side. And then once again, we're going to do the trick with the exponent. So this exponent here, we can really isolate, and we know that the natural log of e is going to fall out. So I'm left with this. So if I finish solving for t, I will get t equals the natural log of 2 over 2,660 divided by the natural log of 1/2. So now I'm finally at a point where I can plug this into a calculator. So I get 10.377, and so that is years. So this is going to be a little over 10 years before the number of cases are down to 2,000. So that's it for this particular problem. Any questions, you can always leave a comment. Otherwise, thanks for watching, guys. I'll catch you next time.